3, modeling real-world data with matrices. So, what is a matrix, other than a really awesome movie? A matrix is a rectangular array of terms called elements. The elements of a matrix are arranged in rows and columns and are usually enclosed by brackets. A matrix with m rows and n columns is an m by n matrix. The dimensions of the matrix are m and n. Matrices can have various dimensions and can contain any type of numbers or other information. Here's a 2 by 2 matrix, right? So rows and columns. So 2 rows, these are the rows, and 2 columns. This is a 2 by 5 matrix. 2 rows and 5 columns. 3, 4, 5. This is a 3 by 1 matrix. 3 rows and 1 column. And so each of the terms in the matrix are called elements. So this element is in row 2, column 1. A matrix that only has one row is called a row matrix. And a matrix that has only one column is called a column matrix. A square matrix has the same number of rows as columns. Sometimes square matrices are called matrices of nth order, where n is the number of rows and columns. So a matrix of 5th order would have 5 rows and 5 columns. The elements of an m by n matrix can be represented using double subscript. So A to 4 would name the element in the 2nd row and the 4th column. Use matrix to represent the data, and use a symbol to represent the price of pain reliever in Mexico City. So, a couple of different ways we can do this. So we've got 3 different items. We've got film, painkillers, and a hairdryer. And we've got 4 different cities: Atlanta, Los Angeles, Tokyo, and Mexico City. So we could do a 3 by 4 matrix or a 4 by 3 matrix. There's nothing here that necessarily indicates one way or the other. You can tell how old this textbook is because it thinks that people still use film. Also, I'm pretty sure film is a lot more expensive than that nowadays. So, right, so I don't know, I'm going to do a 3 by 4 matrix, but you could just as easily do a 4 by 3. And I'm going to label film, painkillers, and the hairdryer. And then we have Atlanta, Los Angeles, Tokyo, and Mexico City. And then we put the information in each of these. So the film was 403, 421, 708, and 397. The painkillers, 678, 741, 3657 in Tokyo. Yikes. And 743. And then the hairdryer, 1898, 2049, 6371, and 3225. And so that's a matrix. And then the painkillers in Mexico City, in this case, is the 2nd row and the 4th column. Yeah. Here's matrix. 2 matrices are equal if and only if they have the same dimensions and are identical element by element. They have to have all of the exact same elements in all of the exact same places. Find the values of x and y for which the matrix equation is true. So we need them to be equal. They need to have the same elements in the same places. So y has to equal 2x minus 6, and x has to equal 2y. Hey, it's a system of equations we can solve, right? Can solve this one by substitution. I don't know, take this, plug this in here. Y equals 2 times 2y minus 6, which is 4y minus 6. Minus 4y from both sides. Negative 3y equals negative 6. Y equals 2. Plug that back in there. X equals 4. So 2 and 4 equals 2 times 4 minus 6 and 2 times 2. These matrices are equal because the elements are the same. The sum of two m by n matrices is an m by n matrix in which the elements are the sum of the corresponding elements of the given matrices. So you can add matrices, but you can only add them if they have the same dimensions, because you just add the corresponding elements. So find a plus b if a is this and b is this. So a plus b, right? This is a 2 by 3 matrix, and this is a 2 by 3 matrix. All right, this is 2 by 3, this is 2 by 3. So our sum, a plus b, is going to be a 2 by 3 matrix. And so all we do is we add the corresponding elements. So negative 2 plus negative 6 is negative 8. And 0 plus 7 is 7. And 1 plus negative 1 is 0. And 0 plus 4 is 4. And 5 plus negative 3 is 2. And negative 8 plus 10 is also 2. So all you do is you add the elements that are in the same row and column in each matrix. And it only works if the two matrices have the same dimensions. And subtraction is just negative addition. It's the same thing. Again, only if they have the same dimensions. These are both 3 by 2s. And so C minus D, we're also going to end up with a 3 by 2 matrix. And we do subtract. So 9 minus 8 is 1. And 4 minus negative 2 is 6. And negative 1 minus negative 6 is 5. And 3 minus 1 is 2. And 0 minus 5 is negative 5. And negative 4 minus negative 5 is 1. So, be careful with the negatives while you're subtracting, but otherwise, pretty straightforward. A matrix that is all zeros is called a zero matrix. Bet you couldn't have guessed that one. The m by n zero matrix is the additive identity matrix for any m by n matrix. And so what that means is that if I have some matrix A, B, C, D, and I add the zero matrix, I get exactly the same matrix as I started. That's what the additive identity matrix means. You can multiply a matrix by a number. The number is called a scalar. To multiply a matrix by a scalar, you simply multiply each element in the matrix by that number. So if we have this matrix A, find 3A, all we're going to do is we're going to multiply each element in the matrix by 3. So negative 4 times 3 is negative 12. 1 times 3 is 3. Negative 1 times 3 is negative 3. 3 times 3 is 9. 7 times 3 is 21. 0 times 3 is 0. Negative 3 times 3 is negative 9. Negative 1 times 3 is negative 3. 8 times 3 is 24. All we do is we multiply everything by 3. Easy. Here's where things get a teensy-weensy bit tricky. You can multiply a matrix by a matrix. In order to multiply a matrix by a matrix, you can multiply them if the number of columns in A is the same as the number of rows in B. Okay. And so the way that I remember this, right? So you always write it as rows by columns. So this is 2 rows and 3 columns. This is 3 rows and 4 columns. If the 2 middle numbers are the same, you can multiply them. And as a bonus, the matrix that you get is going to be the leftover numbers. So yes, we can multiply these two because these 2 middle numbers are the same, and our answer is going to be a 2 by 4 matrix. This is a 3 by 4, 3 rows and 4 columns. And this is a 3 by 4. The middle numbers are not the same, so we cannot multiply these. This is very, very, very important, and I guarantee you somebody's going to get this wrong. So, start with itty-bitty matrices here. A, B, and C to find each product. So, AB, we want to multiply. So this is 2 by 2. This is 2 by 3, and this is also a 2 by 3. So, AB, 2 by 2, and 2 by 3, we can multiply these because the middle numbers are both 2s. So I'm just going to rewrite these here to make things a little bit easier on myself. 3, negative 3, 6, 5, or negative 2. And so what you do is you multiply the row of A by the column of B. And we're going to multiply these and add them up. So remember what I said, the numbers left over should tell you what the dimensions of your product matrix should be. So we should end up with a 2 by 3 matrix. And I'll add the brackets at the end because this could get a little messy. So what we do is we multiply the row from the first one and the column from the second one. So we're gonna do 7 times 3. So 7 times 3 and 0 times 5. So we do 7 times 3 and 0 times 5. And we add them together. And that gives us the first element in our product matrix, which is going to be 21. And then we do that for all the other pairs. So now we do 7 and 0 times the second column. So 7 times negative 3 plus 0 times 4. And that's going to be a negative 21. And then we do 7 times 6 plus 0 times negative 2, which is 42. And then we go down to the second row, and we're going to multiply the second row by each of the 3 columns. So 5 times 3 plus 3 times 5 is 30. 5 times negative 3 plus 3 times 4. Negative 15 plus 20 is 5. And 5 times 6 plus 3 times negative 2 is 24. And so that's our matrix. This is our answer. So you multiply the rows of A times the column of B. And you multiply them and add them up. B times C. B is a 2 by 3 matrix, and C is a 2 by 3 matrix. NA, D and E, not possible. We cannot multiply these because the dimensions don't line up. Yes, on your test or quiz, I will give you something like this, and one of your answer is going to tell you to multiply something, and the answer is you can't. That is absolutely a thing that will be on your quiz or test, whatever I decide to do. Is matrix multiplication commutative? What does commutative mean? Commutative means that the order doesn't matter, right? Regular multiplication is commutative. 2 times 3 is the same thing as 3 times 2. The order does not matter. That's commutative. Let's see if that works for matrices. So A times B is going to be 2, 3, 1, 5, and 7, 1, 3, 4. And so we're going to multiply the row of A by the column of B. And so, yeah, I get it backwards sometimes. The row of A by the column of B, which is going to be 2 times 7 plus 3 times 3. And then do that for the second column. 2 times 1 plus 3 times 4. And then do that for the second row. 1 times 7 plus 5 times 3. And 1 times 1 plus 5 times 4. And so that is 14 plus 9 is 23. 2 plus 12 is 14. 7 plus 15 is 22, and 20 plus 1 is 21. Okay, so what if we do it the other way around? What if we do 7, 1, 3, 4 times 2, 3, 1, 5? So rows of B times the columns of A. And so this is 7 times 2 plus 1 times 1. And then 7 times 3 plus 1 times 5. And 3 times 2 plus 1 times 4. And 3 times 3 plus 4 times 5. And so that is going to be 14 plus 1 is 15. 26. 6 plus 4 is 10, and 9 plus 20 is 29. So, as you can see, these two matrices are not equal. They are different. Matrix multiplication is not commutative. The order matters. This is very, 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 very important. Very important. Order matters. And you can see this in terms of the dimensions too, right? So back here, we have A, which is a 2 by 2, and B, which is a 2 by 3. If we do AB, right, 2 by 2 times a 2 by 3, we can do that because the two middle numbers are the same, and our ending matrix is going to be a 2 by 3. If we did BA, that's a 2 by 3 times a 2 by 2. That's not going to work because the two middle numbers are not the same. So, using these matrices from example 6, we can multiply AB and we get this, but we could not multiply BA. And here we can see that AB is not necessarily equal to BA, and generally is not going to be. Theoretically, there could be some matrices for which AB is equal to BA, but probably only if your two matrices are like identical. Anyways, matrix multiplication is not commutative. Order matters. In football, a player scores 6 points from a touchdown, 3 points from kicking a field goal, and 1 point for kicking the extra point after a touchdown. The chart lists the records of the top 5 all-time professional football scorers as of the end of the 1997 season. Surely that can't have possibly changed. Use matrix multiplication to find the number of points each player scored. So we want to multiply the number of the number of each type of scoring thingy. I'm not a sports person. We want to multiply the number of goals, scoring thingies, by the number of points that they're worth. So, in here I've labeled them. So, we've got our matrix. We take these numbers and we put them in a matrix. And so that's the number of each of the types of attempts. And then we want to multiply that by the matrix for the points. Touchdown, field goal, and the extra point. And then that will give us a matrix with the total number of points. So this is a 5 by 3. This is a 3 by 1, right? It needs to be written as a 3 by 1 instead of a 1 by 3, otherwise we can't multiply them. So, and then what we're going to get is we're going to get a 5 by 1, which will give us the total number of points for each of these 5 people. So, multiply each row of this by each column of the second, which there's only one column. So 9 times 6 plus 335 times 3 plus 943. And this is 0 times 6. All the rest of these are 0 times 6. And this is 383 times 3 plus 562 times 1. And this is plus 373 plus times 3 plus 580 times 1. And this is 385 times 3 plus 526 times 1. And this is 378 times 3 plus 507 times 1. All right, so multiply each row here by this column, and we're going to add them up. And so 9 times 6 plus 335 times 3 plus 943 is a total of 2002 for George Blanda. And then 383 times 3 plus 562 is 1711 for Nick Lowry. And 373 times 3 plus 580 is 1699 for Jan Stenerud. And 385 times 3 plus 526. 1681 for Gary Anderson. And 1641 for Morton Anderson. There we go. And that's it for section 2.3. Tune in next time for transformations with matrices in 2.4.